Okay, so let's take an example of decomposition of dinitrogen pentoxide, which is here. It's 2 moles of N2O5 gas. When it decomposes, it gives 4 moles of NO2 and 1 mole of oxygen gas. Now we can express these changes in concentration. And you see here this square bracket that express molarity. So when you calculate rate of formation of O2, that's going to be positive because it's forming, and this is a delta, means change. This bracket is molarity, concentration of O2 divided by delta, change in time. Same here, rate of formation of NO2. So you see rate of formation, so that means it's positive, and delta is the concentration, change in concentration of NO2 divided by delta T. Now when you check rate of decomposition, disappearance, right, so it's going to get negative. Which one? N2O5. So we use bracket and put concentration of N2O5 divided by delta T. Alright, so that way we can express rate. Now when we relate this expression, now we can relate these expressions by taking into the account of reaction stoichiometry. So what we can do? The formation of O2, concentration of O2 divided by delta T equals 1/4, because 4 moles of NO2 produced, so 1/4 of change in concentration of NO2 divided by delta T equals negative 2 moles of N2O5 decomposed, so negative 1/2 delta change in concentration of N2O5 divided by delta T. So when you see that, it gives average rate over time interval, and you can use instantaneous rate also. So you can definitely use stoichiometry into that account. When you when you calculate instantaneous rate, you need to do experiment. So let's say time 0 second, you get 0 oxygen. At 600 second, you get 0.0021 molarity of oxygen. At 1200 second, you get 0.0036 molarity of oxygen, so and so forth. Now this is experiment. Alright, we express graphically. How do we express? Concentration and time. Time is on x-axis, concentration on y-axis. When it's a formation, it starts from 0 because initially there is no product, no oxygen formation. But when time goes, it starts forming and forming. And when you take a slope, you get concentration of O2 divided by concentration of delta T, and that's where you can calculate instantaneous rate of oxygen. Now let's take a look at another example of S2O8 minus 2. It is in aqueous, and we have, let me erase this one, 3 moles. We have 3 moles of I minus. When it reacts, it gives 2 moles of SO4 minus 2 aqueous and 1 mole of I3 minus aqueous. Now the question is, how is the rate of reaction that is expressed as rate of formation of I3 minus related to the rate of reaction of I minus? So now we are expressing relation I3 minus, 3I minus and I3 minus. That means we need to express stoichiometric coefficient. So the way we can express delta I3 minus, change in I3 minus concentration divided by delta T equals, because here there is a 1 mole, so we don't put any stoichiometric coefficient, but equals, this is negative because I minus 1 is going to be used up, so that's going to be negative 1/3 delta change in concentration of I minus divided by delta T. And that's how we can express rate of reaction for that particular reaction.